Okay, in this part of the analysis we're going to check to see if we can show statistically that there's a significant relationship between the two variables that we're studying, the height and weight of women swimmers. There's two tests for this. One is a t-test and the other is an f-test. In this part we're going to run an f-test. Now, if you haven't already seen the flash file on the t-test, you want to watch that because it gives a little bit of background for the test of significance. Okay, so we are going to run an f-test, and this is going to be based on what's called the f distribution. The f distribution is a distribution of variance, ratios of variances. And it can be used to compare variances, and much the same way that we've used the standard normal distribution and the t-distribution. We're going to set up the null and alternative hypotheses in the same way. We'll assume that beta sub 1 is equal to 0 and there's no statistically significant relationship, and the alternative is that beta sub 1 isn't equal to 0. And if we can reject the null hypothesis, or if the evidence leads us to reject the null hypothesis, then we can go ahead and conclude that. Now, like I said, the f-test, the f distribution, is a distribution of the ratios of variances, and if the null hypothesis is true, that beta sub 1 is equal to 0, there is another estimate of sigma squared, and that is MSR. MSR is SSR divided by, there's formulas in the book for this, the regression degrees of freedom, or actually the number of independent variables. So for simple linear regression, there's only one independent variables, so MSR is actually just SSR. Now, what the F distribution does is that it compares the ratio of these two estimates of sigma squared, the two variances, MSE and MSR. So what we want to first of all do is to look at that distribution and try to find a critical value that we can test on, and then calculate our ratio, our test statistic, and see if we can get a rejection. Okay, we want to go ahead and calculate the MSE and MSR. So MSE is SSE, and we've calculated that before, as 51, and then n minus 2, 5 data points, subtract 2 is 3, so we get 17 for MSE. MSR is SSR divided by 1, and we calculated the SSR as 605. If you look back at one of the other or earlier flash files, we calculated that. Okay, now we're going to go ahead and look at the F distribution. This distribution is a little bit different form to it, and we're going to have a critical value for this. In our problem, we're using alpha at 0.05, so this is going to be an upper tail test, and we're going to find our f sub alpha, or 0.05, from the table. And if you turn in the book to the f distribution table in the back, find that distribution. We're going to look at two things to get our number there for the critical value. The numerator degrees of freedom and the denominator degrees of freedom. Now, F our test statistic is actually the MSR over the MSE. And MSRs, if you look down there at the blue formulas at the bottom of the screen, MSR has 1 degree of freedom. It's in the numerator. So our numerator degree of freedom, I'll just put it, numerator degree of freedom is equal to 1. Our denominator degree of freedom comes from MSE is in the denominator. It's the n minus 2, so our denominator degree of freedom would be 3. And if I look this number up in the table where the numerator degrees of freedoms are the columns and the denominator degree of freedom are the rows, I'm going over to row 3 and column 1, and my alpha value is 0.05. So the critical value for this would be 10.13. My test statistic, calculating this out, would be 605 divided by 17. And 605 divided by 17 is 35.6. So I'm going to reject H sub 0 since 35.6 is greater than 10.13. And therefore I can conclude, as I did with the t-test, I can conclude that there is a statistically significant relationship between these two variables, the height and weight of the women swimmers. Now again, some of the logic of this is that we're assuming that beta sub 1 is equal to 0. In other words, there's no relationship. It turns out that if that's true, then MSR is a good estimate of sigma squared. Now, MSE is usually a good estimate. So if MSR is also a good estimate, then the ratio of MSR over MSE would tend to be 1. The f-test is assuming that that ratio is therefore close to 1 because we're assuming that beta sub 1 is equal to 0, and they would both be good estimates. When we test that against the f distribution, we can see if there's enough evidence to reject that assumption. At alpha equal to 0.05 and our critical value at 10.13, our F ratio, our test statistic, is 35.6. So that is much further out than it had to be to conclude that the ratio of the MSR over MSE is not 1, and that these variances are different. It's also known that if there is a relationship, if there indeed is a relationship, MSR actually becomes inflated. It gets larger. So in the F distribution sense, we're on the upper end of the distribution usually here. We don't split alpha. It's just strictly alpha equal to whatever value we have. In other words, we're running a one-tailed test when it comes to the F distribution.